Okay, let's talk about PySpark. Essentially, it's a really cool way to use Python with the amazing power of Apache Spark. Apache Spark itself is like a super fast engine for processing huge amounts of data, think terabytes or even petabytes. It uses memory as much as possible to speed things up. PySpark lets you write code in Python, but it actually talks to the Spark engine, allowing you to take advantage of all its benefits without needing to wrestle with the more complex Java API directly. It's like having a translator between Python and Spark. Let's talk about what makes PySpark so special. At its core, PySpark uses something called resilient distributed datasets, or RDDs. Think of them as super efficient, fault-tolerant collections that can be split up and processed across a whole cluster of computers. Another important thing is lazy evaluation. It's like saying I'll process this data when I actually need to. This avoids doing extra work. PySpark also excels at working with data in memory, which speeds things up dramatically. And if you're familiar with SQL, you'll love Spark SQL and the Data Frame API, which let you query your data just like a regular database. Plus, it's fantastic for real-time streaming data thanks to Spark Streaming and has built-in machine learning tools too. It really is a versatile powerhouse for big data. Okay, so let's talk about RDD versus data frames and PySpark. They're both ways to handle data on a cluster, but they do things differently. An RDD is like a super flexible container for any kind of data. It doesn't have a set structure when you create it. You define the structure as you work with it using transformations. Data frames, on the other hand, are much more structured. Think of them like tables in a database. The *do* have a schema upfront telling Spark what each column is and its type. This makes querying these datasets incredibly fast, especially when dealing with big data because they are optimized for SQL-like queries. Ultimately, you choose an RDD if you need maximum control, while data frames are your go-to for structured analysis and efficiency. Okay, so let's talk about creating RDD in PySpark. They're the foundation of everything you do with Spark. There are a few different ways to get started. You can use the create RDD method directly, but it's often more convenient to leverage methods like parallelize. Parallelize is fantastic for turning Python lists or other iterable objects into distributed datasets. And if you need to read data from files, text file is your go-to tool. I've shown a quick example using parallelize. Just create a Spark context and then use the method to convert your list into an RDD. It's that simple. Remember, understanding how to create these basic RDD is crucial for mastering Spark. Okay, let's talk about lazy evaluation in PySpark. It's a really important concept for understanding how Spark works efficiently. Basically, when you write transformations like map or filter, PySpark doesn't immediately process your data. Instead, it builds this visual plan and DAG of all the operations you want to perform. It holds off on actually doing anything until you ask it to, usually with an action like count or collect. This allows Spark's optimizer to look ahead and figure out the absolute best way to process your data, saving memory and making your code more readable and flexible. Okay, let's talk about transformations and actions in PySpark. They're super important for working with big data. Transformations are like getting your data ready. You're taking an existing RDD and creating a new one based on it. Think of things like filtering out unwanted rows or changing the format of your data. The cool thing is, these operations don't actually do anything right away. They just create a blueprint for how to process the data later. Actions, on the other hand, are when you finally use that prepared data. They trigger the actual computation and bring the result back to the driver program. So, actions like collecting all the data or counting the number of rows actually execute the transformations we set up. The key difference is that transformations build a plan, while actions actually run it. Okay, so let's talk about the Spark session. It's absolutely fundamental to working with PySpark. Essentially, it's your main entry point into all of Spark's capabilities. Imagine it as a central control panel. It lets you access data frames, SQL queries, machine learning tools, the whole shebang. To create one, you use the Spark Session Builder. You give it an app name. This is just for organization and monitoring, and then tell it where to run. Local asters means it'll run on your own computer using all your available cores. If you're running in a cluster, you'll replace that with the actual URL of your Spark master. Finally, get or create either creates a new session if one doesn't exist, or smartly returns an existing one, so you don't waste resources. Alright, let's talk about getting data into PySpark. One of the most common tasks is reading a CSV file. Think of it as importing data from spreadsheets or text files. We use Spark Read CSV to do this. Just provide the path to your file, and PySpark will figure out the column names for you if there's a header row in the file. The infer schema equals true option is really handy because it automatically guesses what each column should be: numbers, strings, dates, etc. However, sometimes the data isn't perfectly consistent, so explicitly defining your schema can make things more reliable. Okay, let's talk about filtering and aggregation in PySpark. These are super important for getting insights from your data. Filtering lets you narrow down your data frame based on criteria. Think selecting all customers over a certain age or those living in a specific city. You can do this using the filter or where methods. Now, aggregation is where things get really powerful. It's about summarizing data by grouping rows and applying functions like summing sales, calculating averages, finding minimum or maximum values, or counting occurrences. The key here is group by, followed by an aggregate function, often with a new alias for the result. You can even combine filtering and aggregation. First, filter your data to only include relevant rows, then group them and apply aggregate functions. Okay, let's talk about map and flat map and PySpark. They both help us transform data within our RDD, but they handle how that transformation interacts with potentially nested data differently. Think of map as applying a single operation to each item you have. It doesn't change the structure. However, if your transformation function returns another collection like a list or another RDD, that's where flat map comes in handy. It takes all those nested collections and flattens them down into one single RDD. So, when you need to process lists of elements within other elements, flat map is often the right tool for the job. Okay, let's talk about reduce by key in PySpark. It's all about bringing together similar data points. Imagine you have a dataset with different values associated with each unique key, maybe customer ID or product categories. Reduce by key takes that RDD and groups all the records that share the same key, then applies a function to combine those values within each group. It's like a super efficient way to consolidate related information. First, Spark partitions your data by the key you choose, then it performs the reduction locally on each partition using the function you specify, often something simple like adding up all the values for that particular key. Finally, Spark shuffles and merges these local results together to give you a final result for every unique key in your RDD. Let's talk about broadcast variables in PySpark. They're super useful for optimizing your code. Basically, a broadcast variable is like a single copy of some data that gets sent to every worker node in your Spark cluster. This avoids having to send the same information repeatedly, which can be really slow when you're dealing with large datasets. You typically use them for things like big lookup tables, or if you have configuration settings that multiple tasks need access to. For example, if you're mapping ID to names and there are a lot of ID, broadcasting the ID to name map will be much faster than sending it separately to each task. It's all about efficiently sharing data across your cluster. Okay, let's talk about accumulators in PySpark. They're super handy for tasks where you need to combine data from multiple workers across your cluster. Basically, an accumulator is like a shared counter or sum that Spark takes care of updating and combining. It starts with an initial value, and each task can call its update method to add to it. Finally, after all the work is done, Spark handles the reduction process, bringing everything together into one final result. It's a really useful way to aggregate data in a distributed environment, for instance, counting rows or summing values across executors. Okay, let's talk about how to handle missing data in PySpark. It's a really common situation. You'll always encounter null values in your datasets. First, you need to find them out using tools like isNotNull or isNull. Then, you have a few choices. You can drop the rows that contain those nulls, which is okay if they aren't too numerous. Or you could fill them with something else, maybe the average value for a numerical column, or unknown for a categorical one. Another option is to create a new column to flag where data was originally missing. This way you can account for those cases in your analysis later on. Okay, let's talk about caching and persistence in PySpark. Persistence is essentially saving your data in RDD or data frame to disk so you don't have to recompute it every time you need it. It's like creating a snapshot. There are different write modes you can use to control how the data is saved, like overwriting existing data or appending new data. Now, caching is a specific type of persistence that stores your data in memory for faster access. It's great when you have transformations you'll be using repeatedly. Think of it as temporarily storing something to avoid redoing the work. Just keep in mind that caching uses up valuable memory. Okay, so when it comes to running PySpark, you've got a bunch of different cluster managers you can choose from. The most common one is Yarn. It works really well if you already have a Hadoop setup. Mesos is another option that's good for resource management. Kubernetes has become super popular lately because it handles scaling things up so well, and PySpark integrates nicely with it. And of course, there's always standalone mode, which is great for getting started locally. Finally, many cloud providers like AWS and Azure offer managed Spark services that make setting everything up a lot easier. Okay, let's talk about joins. In PySpark, joining data frames is a really important skill. It's how you combine data from different sources to get a complete picture. There are several types of joins, and each does something slightly different. We've got inner joins which only return rows where there's a match on a shared column, left outer joins which keep all the original rows and are matching data from the other data frame if it exists. Right outer joins do the same but for the right side. Full outer joins bring in asterisk. All asterisk rows from both data frames with null values when there's no match. And then we have cross joins, which can create a massive amount of data if you're not careful. The syntax is pretty straightforward. You use join and specify the data frame to join with, a column to join on using on, and the type of join using how. Don't forget aliases if your data frames have columns with similar names. It really helps keep things clear. Okay, let's talk about window functions in PySpark. They are a really cool tool that lets you do calculations across related rows rather than just grouping them into distinct groups like you would with a regular aggregate. Imagine calculating an average price over the last few days for each product. Window functions make that easy. You define these windows using something called over in your SQL, and it tells Spark how to break up your data and what order to consider within those segments. There are parts like partitioning, grouping your data, and ordering, which dictates how the rows are arranged inside those groups. Then you specify the window frame itself, which is essentially the size of the window over which you want to calculate. It's a bit technical but incredibly useful for things like moving averages, running totals, or any time you need context beyond just each individual row. Okay, let's talk about something super important in PySpark: data partitioning. Think of it like dividing a big task among multiple workers. In Spark, each partition is a piece of your data that can be processed independently across different nodes in the cluster. This parallel processing dramatically speeds up your computations, especially when you're dealing with huge datasets. It's also key to scaling your application as your data gets bigger. Spark uses this partition information to decide how to split up work and make sure things run efficiently. You can control how data is divided using methods like repartition or coalesce. Getting the partitioning right is really important for making your PySpark applications perform well. Okay, let's talk about making your PySpark jobs run faster. The first thing to think about is how your data is divided up. We call that partitioning. Make sure it's spread evenly across all the workers in your cluster. Next, you need to tweak some Spark settings like the amount of memory each worker has and how many cores they use. Don't forget about file formats. Using Parquet or OSI can save *10 of time by storing data more efficiently. Caching frequently used data is another great trick. It avoids redoing calculations. And finally, for small datasets, broadcasting them to all workers can drastically reduce network overhead. Remember that optimization isn't a one-time thing. You need to keep an eye on your jobs and adjust things as needed. Okay, so let's talk about saving your PySpark data frames to Parquet files. Parquet is an awesome format. It's really designed for handling massive amounts of data efficiently. The most straightforward way to write a data frame to Parquet is using the df-write-parquet method. You just pass in the path where you want the file saved, and Spark will take care of the rest. You can control how things are handled if there's already a directory there with the same name, for example. You might overwrite existing files or append to them. And don't forget about compression. Snappy is often a good starting point for balancing performance and data size reduction. Okay, let's talk about narrow and wide transformations in PySpark. Think of your RDD like a big pile of data. Narrow transformations are like taking one piece from that pile and doing something to the whole thing. It's efficient because it doesn't move around much. They work on just one partition at a time. Examples include filtering or mapping each partition individually. On the other hand, wide transformations are more like spreading out the entire pile across multiple tables and then combining them. These often involve shuffling data, which can be slower. Examples are things like grouping all the items together or joining two datasets. Knowing whether a transformation is narrow or wide helps you understand how much data needs to move around in your Spark cluster and ultimately optimize your processing. Okay, let's talk about tackling those pesky PySpark debugging situations. It's not always straightforward because Spark runs across many machines. The first step is to really understand what's going on. Don't just look at the error message, dig deeper. Then try to recreate the problem in a smaller setting, like your local machine, so you can isolate exactly what's causing it. Next up, the Spark UI is absolutely essential. It gives you a bird's eye view of how your job is progressing and where problems might be lurking. Pay close attention to those long-running stages or tasks. Strategic logging throughout your code using Python's built-in tools can really help you track what data is doing as it moves through the application. And don't forget to check your input data. Bad data can lead to all sorts of unexpected issues. Finally, keep an eye on the logs from each executor if a stage or task fails. Okay, let's talk about a really important part of Spark, the Catalyst Optimizer. Basically, it's Spark Smart Query Planner. It doesn't just run your SQL instructions as they are. Instead, it figures out the most efficient way to execute them. Imagine a detective solving a case. Catalyst analyzes all the clues your query and determines the best path to reach the solution, the fastest execution plan. It uses techniques like rule optimization, simplifying queries by applying logical rules, and cost-based optimization, which estimates the costs of different approaches and picks the cheapest one. And it's particularly good at handling skewed data where some values appear much more frequently than others to make sure your Spark jobs run smoothly. Understanding how Catalyst works is a key skill for any PySpark interviewer. Okay, let's talk about Tungsten. It's a really important part of modern PySpark. Think of it as Spark's secret weapon for speed. Tungsten is the super efficient engine that handles how your data gets processed. It does things like dynamically splitting your data into pieces to make sure every executor has its work, and it pushes filters right down to the source files so Spark doesn't have to read everything. It also uses smart estimates to figure out the best way to do things. Basically, Tungsten makes PySpark a whole lot faster, often by 2 or 3 times better than older versions. It's one of those behind-the-scenes changes that can make a massive difference in your Spark applications. Okay, let's talk about skewed data in PySpark. It's a really important concept to be aware of when you're dealing with large datasets. Basically, skewness means some values are much more common than others. This can mess up your analysis and make things biased. So how do we fix it? Well, there are a few strategies. We can use sampling techniques like stratified or reservoir sampling to create balanced subsets. Another approach is data transformation. Things like log transformations can help normalize the distribution. We can also bin the data into groups, or if we have extreme outliers, we might need to handle them by either removing or transforming them. And finally, using statistical methods designed for skewed distributions, such as the median instead of the mean, can be really helpful. The key is to understand why your data is skewed and then choose the right technique to address it. Okay, let's dive into running your PySpark jobs on a real cluster. It's not just about writing the code, it's about getting it to run efficiently across multiple machines. First, you need to tell Spark which cluster manager to use, typically Yarn or Kubernetes. Then you configure Spark with the right URL and credentials for that specific cluster. The Spark submit command is your main tool here. It's how you launch your jobs. You'll specify where the application JR lives, along with important parameters like the master URL, which points to the cluster manager and resource requests. Think about memory and cause for both the driver program, the one that coordinates everything, and the executors which do the actual work. Monitoring is also key. Spark's web UI or other tools help you keep an eye on things, so if something goes wrong, you can debug it quickly. Okay, let's talk about keeping your PySpark jobs running smoothly, specifically how we manage memory and resources. Think of it like this. You have a team, your executors working on a big project, your data. If everyone's trying to juggle too much at once, things slow down and eventually crash. Partitioning helps divide the work evenly, so no one gets overloaded. Then, for small datasets that need to be shared across all the team members, we use broadcast variables. This is like handing out a single copy of an important document. Caching comes in when you're reusing data repeatedly. It's like keeping a handy reference sheet around. And finally, adjusting how much memory each team member executor gets. That's executor configuration. Don't over-allocate resources. Checking the Spark UI is super helpful for spotting any bottlenecks, so you can adjust things and keep your PySpark jobs running efficiently. Okay, let's talk about how PySpark handles data when it moves around, specifically how it makes sure your data gets from your main program, the driver, to the worker nodes. The secret is Java serialization. Basically, PySpark turns your Python data into a series of bytes-a-byte stream and sends it across the network. When it arrives at the executors, they reverse this process and turn those bytes back into usable data, allowing them to perform their tasks on that information. It's like sending a package. You serialize everything before shipping it, and the recipient unpackages it when they get it. Keep in mind that serialization can add some overhead, so if you're dealing with really huge datasets, it's something to be mindful of. And remember, all the data needs to be serializable in Java for this process to work smoothly. Okay, let's talk about creating user-defined functions, or UDFs, in PySpark. Essentially, UDF allow you to bring your own custom Python logic into your Spark jobs. Think of it as adding extra tools to your toolbox. First, you define a regular Python function that does what you need. Then, you register that function with Spark using Spark UDF. This creates a link between the function name and its Python implementation. Finally, you can use this registered UDF in your data frame operations, like transforming a column's values. I've shown a simple example here that converts strings to uppercase. Keep in mind that while powerful, UDF can sometimes slow things down, so it's good to optimize them if performance is critical. Let's talk about how we handle different data types in PySpark data frames. It's really important to know how to convert between them, and there are a few key methods you can use. The most straightforward is a type, which lets you directly change a column's type, for example, turning a number into a string. Cast provides more powerful and flexible conversions using Spark SQL expressions. And if you need to work with pandas, we have functions like toPandas and fromPandas to easily switch between the two frameworks. Just keep in mind that when converting data types, there's always a possibility of losing information, so make sure your target type is suitable for the original data. Okay, let's talk about checkpointing in PySpark. It's a really important technique for making your jobs more robust and reliable. Basically, checkpointing is like taking snapshots of your data transformations at regular intervals. It saves the state of your job to persistent storage, so if something goes wrong and your job crashes midway, you don't lose all the work you've done. It's especially useful for really complex jobs that take a long time to run or involve lots of steps. You should definitely use it when you have large datasets and are prioritizing fault tolerance. Avoiding data loss is key. Okay, let's talk about the really important distinction in PySpark: how we handle streaming data. Traditional Spark streaming used what are called D-streams. It breaks down the continuous flow into small batches of data, like little snapshots. Think of it as many batches of processing. It's good for simple stuff, but can get tricky when dealing with out-of-order events and complex state management. Structured streaming changes things up completely. Instead of those micro batches, it treats streaming data as a continuous table, just like you'd find in a relational database. You define what transformations you want to apply using SQL or data frames, and Spark takes care of the details. This declarative approach makes it much easier to build robust applications with built-in fault tolerance and exactly want semantics, which means your data isn't lost or duplicated. Plus, managing state, keeping track of things over time, is significantly simpler. Basically, structured streaming provides a more powerful and streamlined way to work with streaming data in PySpark. Okay, let's talk about watermarking. It's a really important technique when you're working with continuous data streams in PySpark structured streaming. Essentially, it helps us deal with the fact that data doesn't always arrive perfectly on time. Imagine packets being delayed or processing taking a little bit longer than expected. Watermarks are like markers in time. They tell us this record is considered valid and should be processed. When we're using windows, which you might have seen before, watermarking works hand in hand with those windows to decide whether to include late data or drop it. It's particularly useful when dealing with aggregations, preventing incorrect results caused by out-of-order information. And the really clever part is that PySpark allows for adaptive watermarking, where the system learns how long it usually takes and adjusts the watermark accordingly, making everything more reliable. Okay, let's talk about how to handle real-time aggregations in PySpark streaming. The core idea is micro-batching. We break the incoming stream into smaller chunks for processing. Then, we use windowing functions on these batches. Windowing lets us apply calculations like sums or counts within a specific time frame, such as every minute. To do this effectively, especially when calculating running totals or averages, we need stateful operations. This means keeping track of data between batches so we can build up those aggregates over time. Think about an example counting the number of events per minute. We define a window that's 1 minute long and then use a function to count how many events fall within each of those windows, giving us a running count for each minute. Okay, let's talk about a really common PySpark question: the difference between with column and select. Basically, with column is how you add new information or columns to your data frame. It changes the original data by building on what's already there. On the other hand, select is all about picking out specific columns. It doesn't modify your original data frame, it creates a brand new one with just the columns you need. So, if you want to add something new, use with column. If you just want a subset of columns, go for select. Got it? Okay, let's talk about how a PySpark job actually gets done. It starts with you submitting your application. Think of it as telling Spark what to do. Then the driver program kicks in. This is like the boss directing everything. It tells Spark where to find the data, and then the cluster manager figures out which machines need to be involved and assigns them executors, which are basically worker bees doing the heavy lifting. Data gets broken down into chunks and moved around as needed, often shuffling it between those executors. Finally, each executor does its part, sends the results back, and the driver combines everything to give you the final answer. Okay, let's talk about data frame schemas in PySpark. Think of a schema as the skeleton for your data. It tells Spark exactly what to expect from each column. It defines things like the column's name, the type of information stored there, and whether that column is allowed to be empty. While PySpark can usually figure this out automatically when you read data, explicitly defining the schema can really speed things up, especially with large datasets, and helps ensure your data is consistent. You can create a schema using something called struct type, which lets you specify each column's name, its data type like integer or string, and whether it's allowed to have missing values. Okay, let's talk about adding new columns to your PySpark data frames. It's not as simple as just adding a column like you might in SQL. Instead, we use the withColumn method. That's our main tool. You can also rename existing columns using withColumn renamed. Basically, withColumn lets us create new columns based on calculations or transformations of existing data. Okay, so let's talk about renaming columns in PySpark. It's a really common requirement when you're working with data. Maybe you want to standardize column names or just make them more descriptive. There are actually two main ways to do this. First, you can use the withColumn renamed method. This is pretty straightforward. It takes the old name and the new name as arguments. Then there's select expr, which allows you to effectively create a new expression that essentially renames the column. Both of these methods will rename your columns, so pick the one that best suits your style or readability preferences. Let's talk about dealing with duplicate rows in PySpark, a really common interview scenario. The easiest way to remove them is using drop duplicates. This function simply finds all the columns where the values are identical across all rows and removes any duplicates based on those columns. Another approach, which can be more efficient sometimes, is to first use the duplicate method to create a duplicate version of your data frame, then immediately apply drop duplicates. Finally, you can group by all the columns and count the occurrences. Then filter for groups that have only one row. These are your unique rows. Okay, let's talk about repartitioning in PySpark. It's a really important technique for making your Spark jobs run faster. Basically, when you have a huge dataset, just spreading it evenly across all the workers in your cluster is key to efficiency. Repartitioning is how we do that. It ensures each worker gets roughly the same amount of data, preventing some from being bogged down while others are waiting. It's especially helpful if you've got skewed data where certain values appear much more frequently than others. This can cause uneven partitions and slow things down. There are two main ways to do it: repartition, which always shuffles the data, and coalesce, which tries to reduce the number of partitions by merging adjacent ones when possible. That's often a bit faster. Okay, let's talk about coalesce in PySpark. It's all about managing how your data is divided up for processing. Think of it as a way to shrink down the amount of data each worker has to handle at once. By reducing partitions, basically splitting your data into smaller chunks, you can make sure your executors aren't overloaded with memory and that everything runs smoothly and efficiently. It's great for optimizing memory usage, boosting parallelism, and minimizing network traffic between your Spark nodes. The cool thing is coalesce is conservative. It won't ever create more partitions than what you started with. Okay, let's tackle how you'd find distinct values in a PySpark data frame. It's a really common question during interviews. The easiest way to do this is using the distinct method on your column. You simply select the column name and call distinct on it. This returns a new RDD containing only those unique values, making it a super quick and efficient solution. Okay, let's talk about sampling in PySpark. It's super handy when you have massive datasets and you only need to work with a smaller portion of them, like for testing or exploring patterns. We use the data frame sample method for this. You can specify how much of your data you want to keep using the fraction parameter. For example, if you set it to 0.2, you'll get approximately 20% of the rows. The with replacement flag controls whether a row can be selected more than once, useful when you need a truly random subset. And finally, setting a seed ensures that your sampling is consistent across runs, which is really important for debugging and reproducibility. Okay, let's talk about cache and persist in PySpark. They both help speed things up by storing your RDD or data frames in memory. But there's a crucial difference. Cache is like a temporary shortcut. It only keeps the data around while you're actively using it with an asterisk this asterisk Spark session. It doesn't stick around if the driver crashes. On the other hand, persist is more robust. It not just stores the data in memory, but also saves a copy to disk so it's available even if your application restarts. You can even control how durable that saved copy is. So, if you need to be sure your data survives a crash, go with persist. Cache is great for when you know you'll access the same data repeatedly within the same session. It's about speed and efficiency in those specific moments. Okay, let's talk about schema evolution in PySpark. It's all about how you handle changes to your data structure. Think of it like a growing tree. As your data comes in from different sources or as business requirements shift, the columns and types might change. Schema evolution allows you to adapt your Spark jobs without breaking existing code. It's super important because data never stays static, and you want your applications to be flexible enough to handle those changes gracefully, like adding new features to a growing application. Okay, let's talk about how to bring your own custom logic into PySpark SQL. You've probably heard of user-defined functions, or UDFs. Think of them as little pieces of code you write that can be used right within your SQL queries. The first step is registering the function with PySpark. Essentially, you tell Spark, hey, I have this function, here it is. You do this using Spark UDF register. You provide a name for your function and, most importantly, what type of data it returns. It's crucial to define these things correctly. Let's see an example. We've defined a simple function called myDouble that just doubles its input. Then, using Spark UDF register, we tell Spark about this function and specify the return type as an integer. Finally, you can actually use it in your SQL queries, like selecting the doubled values from a column. Okay, so let's talk about reading JSON files into PySpark data frames. It's a really important step when dealing with data that comes in this format. The process is surprisingly straightforward. You start by creating your Spark session. Think of it as the gateway to all things PySpark. Then, you use the session read JSON method, providing the path to your JSON file. PySpark cleverly figures out the structure of the data and creates a data frame for you. If you need more precision over how the structure is interpreted, you can define the schema directly. It's really simple once you get the hang of it. Okay, let's talk about explode in PySpark. It's a really handy function when you have columns that contain arrays like lists of numbers, strings, or anything else. Basically, it takes each element inside those arrays and turns them into their own separate row in the data frame. Think of it as expanding your data. For example, if you had a column with a list of ages for different people, explode would create one row for each person and each age they have. Okay, let's talk about handling nested JSON in PySpark, a really common scenario when you're pulling data from external sources. PySpark gives us some excellent ways to tackle these complex structures. First off, we have JSON normalize, which is great for flattening everything into a nice tabular format. Then there's select expert, allowing you to specify paths within the JSON using expressions like $address street, really powerful for targeted extraction. Finally, PySpark's built-in flatten function can handle multiple levels of nesting and put them all in one column. I'll show a quick example here demonstrating how we can use flatten to get the street address from our nested JSON data. Let's talk about a really important distinction when working with PySpark data frames: the difference between group by and group by key. Group by is like creating smaller, more manageable groups of your data based on some column. It gives your data frame as output, where each group is its own associated data frame containing all rows that belong to it. This is great if you want to do calculations or transformations within those groups. On the other hand, group by key creates a much larger RDD structure, basically a collection of keys and their corresponding values, which are iterables of all rows. It's powerful when you need to access individual records within each group, but it can become memory intensive with large data sets. So, consider your needs. If you're mainly aggregating within groups, group by is typically more efficient. If you need to work directly with the individual records in a group, then group by key might be necessary. Just be mindful of potential memory limitations. Let's talk about accumulators in PySpark. They are like persistent variables that let you accumulate values across your data. Think counting things or summing up totals. It's a really useful technique, especially when you don't want to shuffle the data around. However, there are some important limitations. Accumulators can only be updated once per partition, and they aren't designed for concurrent updates. So while they are fantastic for simple counts, consider Spark's built-in aggregation functions if you're doing something more complex. Okay, let's talk about running PySpark jobs on Yarn. Yarn is basically how Spark manages its resources within a large Hadoop cluster. First, you need to tell your Spark session that it's going to use Yarn. You do this by setting the Spark master property to Yarn. Then, when you submit your job, you'll use Spark Submit. A common way to submit is with deploy mode class, which is great for production environments. If you're just experimenting or debugging, deploy mode client can be easier. Yarn then automatically allocates the resources like memory and CPU cores that your job needs from the cluster. Okay, let's talk about broadcast joins. They're a really smart way to optimize your PySpark queries. Basically, if you have a large table and a much smaller one that you're joining with, PySpark can copy the small table to every worker node instead of shuffling everything around on the network. This drastically reduces data movement and speeds things up considerably. You'll want to use this when you're joining a big table with something relatively static like product categories to customer details, for example. It's all about avoiding that costly shuffle operation. Okay, let's talk about union operations in PySpark. There are essentially two ways to combine data frames, union and union by name. The key difference is how they handle columns. Union demands that both data frames have exactly the same schema, meaning identical column names and data types. If they don't match, you'll get an error. Think of it like merging two spreadsheets where every column has the same heading. Union by name is more forgiving. It uses the column names to figure out how to combine the data frames, even if the columns have different names or types. PySpark will try to convert data types to match, but be aware that this could lead to unexpected results if not handled carefully. It's a good practice to check your schema and data types before performing any union operation. Let's talk about a common PySpark interview question: the difference between union and union by name. Basically, both combine data frames, but they handle column names differently. Union is super strict. It requires your data frames to have exactly the same schema, meaning identical column names in the exact same order. If there's even a tiny mismatch like a case difference or a different column order, you'll get an error. On the other hand, union by name is much more forgiving. It matches columns based on their name only, ignoring case and order. If one data frame has a column that the other doesn't, it simply skips that column during the union. So, if you're working with data frames that might have slightly different schemas but you want to combine them based on the meaning of the columns, union by name is your go-to choice. Let's talk about sorting data in PySpark. It's a really common question you might hear in an interview, and it shows that you understand how to manipulate your data frames effectively. There are actually three main ways to sort: order by sort. They're basically the same thing. And then there's order, which gives you even more control, like sorting in descending order or specifying multiple columns at once. The order by method is your go-to for simple ascending sorts, and if you need to reverse it, just use desc on the column name. Okay, let's talk about order by versus sort in PySpark. Both are used to arrange your data, but they work a bit differently. Think of order by as a suggestion. It tells Spark that you want the data sorted, but it doesn't actually do the sorting until you really need it, like when you join or filter on those columns. Sort is more direct. It immediately goes out and sorts the entire data frame in memory. Because of that immediate sorting, sort can use up a lot more memory, so generally, order by is the preferred method for better performance and efficiency, particularly with large data sets. Okay, so you've got a PySpark data frame and now you want to use pandas. Luckily, converting between the two is pretty straightforward. You can leverage Spark create data frame for this. It takes an RDD, which is Spark's distributed data structure, and essentially creates a new pandas data frame from it. You provide the schema so that Spark knows what each column represents. It's important to be mindful of the size of your RDD, as very large ones can impact performance during conversion. Also, pay close attention to data types. Make sure they align between Spark and pandas. Okay, let's talk about how a PySpark application is structured. It's really all about this dynamic duo, the driver and the executors. The driver is like the conductor. It sets up everything, tells everyone what to do, and gathers the final results. It creates the Spark session, allocates resources, and schedules tasks. Then you have the executors. These are your worker nodes that actually do the data processing in parallel. They receive instructions from the driver and then crunch away at the data, sending their processed results back to the driver. Let's talk about a common snag you might run into when loading data in PySpark: schema mismatches. Basically, the way your data is structured in the file doesn't quite match what PySpark expects. The first step is to figure out exactly why you're seeing an error, usually something like a type mismatch or an invalid field name. The best approach? Be explicit. Define a clear schema using PySpark's PySpark SQL types module, telling PySpark exactly what each column should look like. You can also use infer schema, but be careful with that. It's helpful, but sometimes throws off results. Don't forget to consider how you want to handle missing values. Explicitly setting the null value is often a good strategy, and always clean your data before loading it into a data frame whenever possible to avoid these problems down the line. Okay, let's talk about pivoting data in PySpark. Pivoting is a really handy way to reshape your data frame, essentially turning long format data into a wider layout or vice versa. You've got two main tools for the job: pivot and pivotal. Pivot is straightforward. It creates new columns based on unique values from an index column, aggregating data from another column. Pivotal is similar but handles missing values a bit better by letting you specify what to fill those gaps with, defaulting to null if you don't say otherwise. Let's look at an example. This code groups the data by category and then uses pivot to create new columns for each category, summing up all the values associated with each one. Okay, let's talk about map and map partitions in PySpark. Map is like processing individual pieces of a puzzle separately. It takes one piece at a time and transforms it. It's great for simple transformations where you don't need to see the whole picture. Now, map partitions, however, is different. It grabs an entire puzzle piece and does its work on that whole section first. This is handy when your transformation needs information from all asterisk elements within a partition. Maybe you have to calculate something before deciding what to omit. Okay, let's talk about custom partitioners in PySpark. Sometimes the default way Spark splits your data isn't ideal, especially if you have a lot of uneven distribution. That's called data skew. A custom partitioner lets you take control. It's essentially a class that extends Spark context built-in partitioner. You define how it breaks up your data based on whatever criteria matter most to you, maybe aligning with certain key fields or even business rules. It's really useful for avoiding those performance bottlenecks caused by some tasks taking much longer than others because they get overloaded. Think of it as giving Spark a little nudge in the right direction, and it can drastically improve your processing speed and resource usage. Okay, let's talk about a really useful PySpark interview question: how to count the unique values in a column. The most straightforward approach involves using the distinct and count methods. First, we select just the column you're interested in with select. Then, distinct removes any duplicates, leaving only the unique values. Finally, count simply tells us how many distinct values remain, giving you your final answer. Okay, so let's talk about writing your PySpark data frames directly into Hive tables. It's surprisingly straightforward. You use the df-write method but with a specific format set to Hive. Then, you simply call save as table, passing in the fully qualified name of the Hive table, including both the database and the table itself. This is incredibly useful when you want to integrate your Spark processing with existing Hive workflows and queries. Don't forget that the target database and table must already exist within Hive, so make sure they're set up before running this command. Okay, let's dive into how PySpark handles data. When you're working locally, maybe on your laptop, Spark uses the local file system, which is just your computer's hard drive. This is great for smaller datasets and super easy for debugging. But when you start dealing with really big data, that's where HDFS comes in. HDFS is a distributed file system designed to spread the data across an entire cluster of computers. It's like having multiple hard drives working together to store everything. While it might be slightly slower than using your local drive, it allows Spark to scale up and process massive amounts of information. That's its main strength. Okay, let's talk about the guts of Apache Spark. At its heart, a Spark cluster is built around several key pieces. First, we have the driver program. This is where your application's main logic lives and it orchestrates everything. Then there's the cluster manager, which acts like a traffic controller, making sure each job gets enough resources. Executors are the worker bees that actually do the processing on separate nodes within the cluster. Spark Core provides all the behind-the-scenes services like memory management and scheduling to ensure things run smoothly. Finally, we have RDD. These are basically how data is distributed across multiple machines for parallel processing. Thinking about these components will give you a solid foundation for tackling any Spark interview questions. Okay, so let's talk about how Spark handles failures. It uses something called resilient distributed datasets, or RDDs, which is the foundation of its fault tolerance. Basically, Spark keeps a complete record, a history of every step involved in creating an RDD. Think of it like a detailed recipe. If one worker node goes down, Spark can use this lineage information to figure out exactly how to rebuild that RDD from scratch, using the previous steps as instructions. And for frequently updated data, Spark takes regular snapshots called checkpoints, so if a failure happens between those checkpoints, it doesn't have to recompute everything, it just restores from the last good checkpoint. It's pretty clever, right? Let's dive into flat map values. It's a really handy transformation in PySpark when you need to generate multiple values per key. Think of it as expanding your data by processing the values associated with each unique key. It takes an RDD where keys map to lists, and applies a function to those lists, producing a new RDD where each element is a pair, the original key in a list of transformed values created from its original values. It's different from map values, which just transforms the values themselves, and flat map, which reduces the number of elements. Okay, let's talk about how we actually no asterisk if a PySpark job is running smoothly. It's not enough just to run it and hope for the best, right? We need data. First, there's execution time, simply measuring how long the entire job takes to finish. But be careful, because that can be misleading. Then we look at throughput, which tells us how many records our application is actually processing per second. That's a good sign of efficiency. Latency measures the time it takes for *1* record to get processed, and this is really important if you're dealing with things like real-time data streams. We also keep an eye on CPU utilization. If Spark is maxing out your CPU, that could signal a bottleneck. Finally, memory usage. We want to make sure we're not using up all our resources. Spark UI and tools like Prometheus or Grafana are incredibly helpful for visualizing all of these metrics so you can spot problems and optimize your code. Let's talk about approximate distinct counts in PySpark. When you need to know roughly how many unique values are in a column, especially on very large datasets, the exact count can be extremely slow. That's where approx count distinct comes in. It's a function that gives you an estimate by sampling the data. It's like taking a snapshot of a huge collection and counting how many different items are in that snapshot. It won't be perfect, but it will be much faster than counting everything. The function takes one argument, the name of the column you want to analyze. You can also optionally specify the number of samples to use. More samples mean better accuracy, but they take longer. So, if you need a really precise count and your data isn't massive, go for it. But when speed is critical, approx count distinct is an excellent tool. Let's talk about handling missing data in PySpark. A really important function to know is as null. This function checks if a value in your data frames column is actually null, meaning it doesn't have any information there. It returns true if its asterisk is null, and false otherwise. You can use this to filter out rows where a specific column has missing values. Then you have is not null, which does the opposite. It checks to see if a value is not null and returns true in that case. These two functions are your go-to tools when dealing with potentially incomplete data, helping you keep your analyses clean and focused. Let's talk about converting dates in PySpark, a really common interview question. You'll often find date information stored as strings, and that's okay, but you need to make sure it's actually treated asterisk as asterisk a date so you can do calculations with it. The easiest way to do this is using the toDate function. It takes two things: first, the column containing your date strings, and second, a format string that tells PySpark exactly how the data are formatted in your data. For example, if your dates are EIMMDD, you'd use that as the format string. Pay close attention to your input format because an incorrect format will cause parsing errors. Okay, so let's talk about Spark context. It's a really important concept in PySpark. Basically, it's the starting point for all your work. Think of it as the brain of your Spark application. It connects your Python code to the powerful distributed processing engine. It manages everything from the workers that do the calculations to how resources are allocated. You create one Spark context at the very beginning of your script, and you need to make sure it's done before you start doing anything else. Okay, let's talk about actions and transformations in Spark Streaming. They're really important to understand. Transformations are like building blocks for your data. They take your existing data and create new RDD based on it. Think of map, filter, they all do that. They don't change the original data, just build something new. Now, actions are when you actually do something with that processed data. They're like the final step after you've done your transformations. You might want to count the records, save them to a file, or write them somewhere. The key thing is transformations create RDD and actions use those RDD to get a result. Essentially, transformations build and actions consume. Okay, let's talk about how to handle data loss in PySpark streaming applications. It's a really important topic. When your Spark driver goes down, you can lose all the work that's been done up to that point. That's where checkpointing comes in. Essentially, checkpointing is like taking snapshots of your data and the application state at regular intervals. You trigger these snapshots using checkpoint on your streaming data frame or RDD. PySpark then stores those snapshots in a designated location, usually a default directory if you don't specify one. And here's the brilliant part: if the driver crashes, Spark can automatically recover and resume processing from the last checkpoint it has, minimizing data loss and ensuring reliability. It's important to check frequently enough based on how quickly your data is changing. Balancing durability with storage costs is key. Okay, let's talk about how we handle situations where our streaming data needs to remember things as it moves through the pipeline. When you're dealing with data that builds up over time, like a customer's activity or sensor readings, you often need to track information across batches. That's where stateful transformations come in. PySpark offers several ways to do this effectively. Update state by key is probably the most frequently used. It lets you define a function that calculates the new state based on the current record and what you already know. Then there are methods like reduce by key and aggregate by key, which allow us to combine data associated with each key, updating an accumulator, and functions like map state by key and flat map state by key that let us transform existing state values. It's really important to remember checkpointing, saving your state periodically so if something goes wrong and the pipeline restarts, you don't lose all your progress. And finally, consider your state backend. In-memory might be fine for smaller datasets, but RuxDB is often a better choice as your data grows. Okay, let's talk about a really useful function in PySpark structured streaming called forEach-batch. Think of it like this: your streaming data isn't just a continuous flow, it gets divided into smaller chunks or micro batches. forEach-batch is how you process each one of those batches. It takes two things: a batch ID to tell you which batch you're working with, and a function that does the actual work on the data in that batch. The batch ID is super important because it lets your processing logic react at different stages of the stream. It also receives an offset, basically how far along the data is within that specific batch. This allows for accurate handling if some events arrive later than others. Okay, so let's talk about joining streaming and static data in Spark, a really frequent interview question. The key thing to remember is you have several options. First up is union by name. This is fantastic when your static and streaming data have similar columns, and you just want to add the new streaming records to the old ones. Next, you can use the standard join method, but make sure both your static and streaming data frames are keyed by a common column. Finally, if you're looking for aggregated results, maybe summing things up, you could leverage reduce by key or aggregate by key, combining that with your static data frame as a starting point. Don't forget about Windows. Managing time is essential when dealing with streaming data. Okay, let's talk about getting output from your PySpark streaming queries. There are two main ways to do this. You can pipe it straight to your console using the print function within your transformations, which is really handy for debugging and quick checks. Or, if you want to save it persistently, you'll use the write text or other formats like write Parquet. Remember that the output mode setting, whether you're appending to a file, processing the entire dataset at once, or updating incrementally, significantly impacts your query's performance and how much memory it uses. Okay, let's talk about watermark delays in Spark streaming. Think of it like this: sometimes data isn't exactly when you expect it to be, leading to a slight lag in your processing pipeline. This is what we call a delay. A watermark is basically a deadline that Spark sets for itself, a time by which processing should ideally be finished. Spark uses parameters like min latency and max latency to control how much delay is acceptable. Min latency defines the absolute minimum delay you're willing to tolerate, while max latency represents the maximum amount of delay before data is considered stale and discarded. You can also adjust the frequency at which Spark calculates these watermarks using watermark interval. It's important to understand that choosing these values affects both latency and potential data loss, so pick them carefully based on your application's needs. Okay, let's talk about how PySpark handles data in streaming. One important distinction is between append and complete modes. With append, the stream just keeps growing. New batches of data are added to the existing data frame without erasing anything. This is great for things like continuously updating dashboards where you want to see a rolling history of events. On the other hand, with complete mode, each batch of data is processed and its results are emitted immediately. Once that last batch is done, the stream stops entirely. This is perfect if you need to react to the very latest information, like setting off an alert when a value hits a certain threshold. Okay, let's talk about stopping streaming queries in PySpark. It's really important to know how to do this programmatically, because if you don't, your application can just keep running and eating up all your resources. There are a few ways you can stop a query. The easiest is Spark streams stop, which will halt everything. However, sometimes you only want to stop one specific stream without shutting down the entire app. For that, use stream cancel. And for more complex pipelines which shut down sequences, stream shutdown is your friend. Just remember to handle any potential errors during this process and make sure downstream processes know what's happening. Okay, let's talk about shuffle partitions, a really important thing to understand when optimizing your PySpark jobs. Basically, these are like dividing up all that data moving around during operations like grouping or joining. If you don't control them properly, it can lead to some serious bottlenecks. There are two main ways to adjust them. The first is a global setting called Spark SQL shuffle partitions, which controls the default number of partitions used. Then we have methods like repartition and coalesce, which let us control the partitions within specific data frames or RDD. Repartition adds more partitions, while coalesce reduces them by combining existing ones. The sweet spot for the number of partitions depends on your cluster size and data. A good starting point is often twice the number of cores, but you'll want to experiment to find what works best. Okay, let's talk about setting up Spark configurations within your PySpark code. It's really important to do this right to ensure your jobs run efficiently and use the resources you need. Instead of just specifying things in the command line when you launch Spark, we can programmatically configure it using PySpark. You create a Spark conf object, think of it as your central configuration hub. Then, you use the set method to add individual configurations, like how much memory each executor should have or the number of partitions for shuffles. You can even set multiple things at once. Remember, always pass this configured Spark context when initializing your Spark application, and you'll be good to go. Okay, let's talk about speculative execution, a really clever trick CPU used to boost performance. Basically, they try to guess what instructions you're going to need next and start working on them before they actually asterisk or asterisk needed. It's like anticipating the future. This is particularly helpful in loops or when your code takes different paths based on conditions. However, because it's a prediction, there's always a small chance of getting it wrong, so CPU have built-in safeguards to handle that. Okay, let's talk about a really handy Python function that comes up quite often in PySpark interviews, range. Now, Spark data frames don't directly use range like you might be familiar with from regular Python. But the concept is essential. We often see it used within operations like adding new columns, particularly when we need to refer to row indices. For instance, a common task is creating an ID column for each record. Spark provides functions like monotonically increasing ID that accomplish this efficiently, avoiding the need to manually use range. While not always explicitly visible, understanding how these underlying mechanisms work makes you well prepared for interview questions. Okay, let's talk about dealing with JSON arrays in PySpark. They are super common when you're working with data from sources like logs or API. Often, a column will contain an array of things. Maybe it's a list of user ID or a list of product names. There are a few good ways to handle these. First, if you just need one specific item from the array, you can use getItem, which lets you access elements by their index, like grabbing the first element. Then, if you want to really spread out all those individual items into separate rows, explode is your friend. It turns each element in the array into its own row. Finally, the array function allows you to reorder or combine the elements within an existing array column. Just keep in mind that exploding large arrays can impact performance, so think about whether it's really necessary. Let's talk about how to swap out specific entries in your PySpark data frames. There are a few really handy ways to do this. The replace method is super simple. Just give it a dictionary mapping the old values to their new counterparts. If you need more control, especially when dealing with conditional replacements, when otherwise is fantastic, you can check if a column's value matches something and then assign a different value accordingly. And for really complex scenarios or transformations, map offers even more flexibility. Okay, let's talk about reading data from databases in PySpark. It's a really important skill when you need to combine Spark with existing relational systems like MySQL or PostgreSQL. Essentially, we use PySpark's Spark read JDBC function. You first need to set up the connection details. That includes the JDBC driver class name, the database URL, your username and password. Then, you provide a SQL query to retrieve exactly what you want from your table. Finally, Spark executes the query against the database, and it returns a data frame containing all of the results. It's pretty straightforward once you've got your connection details sorted out. Okay, let's talk about the catalog in Spark SQL. It's a really important part of how Spark understands and works with your data. Basically, it's like a librarian for your database as it keeps track of everything, the names of all the tables, what kind of information each column holds like numbers or text, and most importantly, where the actual data files are stored. When you run a query in Spark SQL, the catalog is consulted to figure out the layout of those tables so Spark can efficiently find and process your data. Okay, let's talk about how to check if two PySpark data frames are exactly the same. It's more complex than just looking at whether they have the same number of rows. First, we need to understand that there are two types of equality, structural and data. Structural equality means the data frames have the exact same columns with the same data type. Think of it like having a blueprint for each data frame. Data equality is even stricter. It means asterisk every single value asterisk in every column is identical across both data frames. The equals method is your best friend here, as it checks for both structural and data equality at once. If the schemas don't match different column names or types, then the equals method will immediately return false. The equals operator only performs a structural comparison. It doesn't care about the actual data. I've included an example to help illustrate these concepts. Okay, let's talk about dynamic allocation in PySpark. It's basically Spark's way of intelligently scaling up or down its computing resources to match the workload. You enable it by setting a configuration flag Spark dynamic allocation enable to true. Then, you need to decide how executors should be allocated and what the total core count should be. There are different strategies like shuffle service and execution mode, each with pros and cons. Finally, you set minimum and maximum executor limits so Spark knows the boundaries of its scaling behavior. A good example would be using conf when submitting a job to specify these parameters. Thank you for watching.